So in this video we're going to be doing a few things, starting off with correcting our two variable names that have been poorly spelled throughout all of these videos and was pointed out to me by somebody. We're looking in detail at static versus dynamic data structures. So far we have been making our abstract data types, and we've been using arrays to store our data, and arrays are brilliant. However, they don't change in size. So if you set off with an array of size 8 and it turns out mid-program you want to have more than that, you're not able to. It's not possible. So we've got dynamic data structures to talk about, linked list visualization, the heap, and going and adapting our program and making a couple new classes for a dynamic stack and a dynamic queue. It's not going to take too long to do that because we've got the general idea of how stacks and queues work, so we won't be doing much of a focus there. It'll just be introducing the idea of our dynamic data structure in there. So something other than an array, something that won't be a set size. So correcting the spelling mistakes, it was pointed out by somebody that my front pointer and rear pointer, it should actually be PTR. We did do PTR in our stack, but I made a spelling mistake, and you can see how easily it just carried on. Many of you didn't notice. So what we're going to do is a find and replace. So I've selected the word that I'm interested in, Control F to get the ability to search through, see all the different instances of it, and if I do this drop down here, I get the ability to replace it. So we're going to replace front PRT with front PTR, standing for pointer, of course, and we can do it for the entire solution, and that means that it's going to change in our other classes as well. Replace all. It's not able to undo it, so confirm again. Yes, 11 places it's changed, and it's just so that it looks a lot nicer. And the same happened with the rear pointer. Just a little error on my part. It doesn't actually change the code. Sorry, it does change the code. It doesn't change the meaning. We knew it to be front pointer and rear pointer, but it's better to have it written correctly. If you do spot any other mistakes, spelling mistakes, do let me know. So you see that we've used the rear pointer a lot more. We've got 14 occurrences of that, and that's it. So you can do find and replace to change our identifier names, etc. So with that bit of housekeeping done, we're going to move on to static versus dynamic data structures. Going a quick brief about them, but we'll go into a bit more detail now. Okay, so static data structures on this left-hand side first of all. We'll look at the first one. They are fixed in size. So once we've allocated a particular amount of memory, it doesn't change. During runtime, it doesn't change. Whilst the program's executing, whilst it's running, it doesn't change in size. So if we allocate an array of size 100, there's 100 spaces of a particular data type in memory. They've all been allocated. A dynamic data structure, on the other hand, is flexible in size, and it can grow and shrink as it's needed. So when we declare a dynamic data structure, we don't have to set a size. There's no need to say it's going to be of this length. It's going to be of this size. Often with the dynamic structures, you can set a maximum, but it doesn't have to be that case. So officially, when we start with a dynamic structure and just declare it, it's got nothing in there. There's no data stored within it, and no space for any data to be stored. Static allocates that data and it's in use. So static, second point, it can waste storage. So if the number of data items is small relative to the size of the structure, so say again we had an array of size 100, but we're only actually using, when we run the program, 32. We've wasted loads of space. That structure is still the size 100, even though we've only got 32 data items in it. Think about our queue. We can add data to it and remove data from it, and we're wasting storage space if we've got a large array but a few data items in it. Whereas a dynamic one only takes up that amount of storage space required for the data. It grows and shrinks, as we said before. So there's no wasted empty space where we're waiting to put data items. However, it's not all great for dynamic. Static typically don't need pointers, so can potentially use less space and memory. And that potentially is if the dynamic and static data structures are of the same size. So if we have 8 items in an array, and we have 8 items in a dynamic data structure, the dynamic data structure typically require more memory to store it, and we'll see more as to why that is next, but it's about storing pointers to the next item. And that's really because this last point here, a static structure is typically stored in consecutive memory locations. So we will start the array will start at a particular memory location. So that'll be index 0, then index 1, 2, 3, 4, 5, however many will be stored consecutively. There are times in which that's not true, but generally speaking, or typically, that's the case. Dynamic, however, they don't get stored in that way, typically. They can still be, but you don't necessarily store them in that way. They could be stored in memory locations all over the memory. They don't have to be stored consecutively, but because they're not stored consecutively, it can be more time consuming to return data from a dynamic data structure than a static one. So summarize, dynamic, brilliant because lack of wasted space. We can grow and shrink our data structure. Static is static and doesn't change, so we're wasting space if we don't fill that data structure, and we can't go any beyond the bounds of that data structure as well. We can't add any more data. Dynamic data structure has to store pointers as well, so it may require more memory for the same size. So if you did have something of the same size, 8 items in the static data structure, 8 items in the dynamic one will take more memory. But, as we saw the advantages before, the dynamic one would be able to store more than 8, whereas the static would be stuck with, let's say, 8 again, as an example. And finally, stored in consecutive memory locations, the static one, whereas dynamic doesn't. And we're just going to see that in action in a moment. So we're going to be looking at two particular types. So we've got static and we've got an array, and we've got dynamic, and it's going to be our linked list. So our array, first of all, as we mentioned before, fixed size. So we've gone for the size of 6 in this example. And so indexes from 1 to 5, from 0 to 5, I apologise. And they would be stored at consecutive memory locations in the RAM, or whatever memory source you're using, so that when you've got an array, your program can point to where that array starts and immediately know the addresses for all of the items in the array. So if you wanted the array at index 4, for instance, you knew that whatever the address in memory is, so let's say for example this is 140, the data item at position 4 in the array, so the 5th item in the array, would be at memory location 144. There's no searching needs to be done. We can just tell that based on our index. So array stored at memory location 140. The 5th item in that array would be stored at 144, typically. And we can access all these array positions and put some data in, 5, 4, 3, 2, and put some data in there, and you can see, for example, we've got those wasted spaces. If we don't use all of the array positions, we're still using these locations in memory, even if we do not put any data in them. That's how our array is working. Our dynamic linked list, well, we'll again have, when we declare our linked list, we'll have some sort of pointing device indicating where in memory we have started this list. So let's pick another memory location. Let's go for 214. So memory location 214 is where our dynamic linked list is stored. But instead of just the data item, so I'm going to use the same data as we have in our array, instead of just the data item, we've also got to have some form of pointer. And because this is dynamic, until we start adding to our dynamic data structure, there isn't anything already there. We've put one item in there now, and that's pointing to nothing. But we could introduce another data item. And what's going to help us do that is something called the heap. The heap is a large pool of memory which allocates memory to programs when they request it. So if we were adding 4 to our dynamic data structure, we'd request some memory from the heap, and then we'd have our previous data item point to that position in memory. So we're storing not only the data item, not only the 5 like we had in the array, but a pointer as well to the next memory location where we can store a 4. And again, our program introducing a 3 like we've got in our array, we request some memory from the heap. The heap gives us some memory, and then we have our pointer pointing to the next item in our memory. This time the 3. And again, we can keep going with that. We request some memory from the heap, and then we point to the next data item, and it keeps on going. But the heap won't necessarily give us consecutive memory locations like we've got an array. When we've got an array, we request an array of a certain size. It gives us a block of memory that's going to be that size in consecutive memory locations. The dynamic might not always be memory locations directly one after the other. So, for example, we start our linked list here at position 214, but this could be pointing to 256. The next one could be pointing to 310. The next one could be pointing to 411. We can ask the heap for some more memory, and we could store an additional number, 1, and that could be at memory location 32. So it doesn't even have to be all memory locations after, depending upon what memory locations are free in the pool of available memory that the heap has got. You can request chunks of memory from the heap. Now, if we start to put 1 in our static array and 0, our static array, we've run out of space, we can't do anything else. But with our dynamic data structure, we can just request more data from the heap and put more data items in. And we can keep doing that, requesting more data from the heap. And we point to another memory location and put some more data in. Request more from the heap. Put some more data in. Request more from the heap. Put some more data in. And every time the previous item in our linked list points to the next one, request some data from the heap, point to it. And we are not limited in size. We can we are limited in size, as we'll see in a moment, but not limited in the same way a static array is. A static array, once it's been declared as this array size 6, it's going to have that for its lifetime. It can't grow and shrink. Our dynamic one here is visually growing. We can keep requesting. I don't know why I'm decrementing, it's just started it, and so on. And if it doesn't actually point to anything, just some sort of null pointer, null pointing to nothing, but it could carry on. But if we were looking to get array with the index of 4, so the 5th position in the array, looking to get 1 in the array, really quick and easy to access. In the dynamic linked list, well, we've got to go from the start and go, right, what do you point to? 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 Right, we're here. So 1, 2, 3, 4, 5, 5th item to get what we're looking for. So it can be slower to access a dynamic linked list than a static array. So the dynamic linked list is brilliant for memory use. If we're not using that much memory, we can shorten it. If we want to go to get more memory, we can. Static, not too good at that. It's fixed in size. So if you're not using all the positions, you're just not using all the positions, but you are using memory. You're taking space in memory. In terms of access and maintenance, the static array is going to be far easier. But we can do some unique things with the linked list that make it a bit better than our static array. For example, if we were doing a queue here, if we were having a queue, and we're using an array or a linked list for the queue. If we wanted to, the 5 was the first thing in the queue, and as we've seen in a video before, we had a shift going on. If we didn't use a circular queue, we could shift everything up. So we could take a copy of 5 and then shift the 4 up, the 3 up, the 2 up, the 1 up, the 0 up. Now that's taking a lot of processing to do that. That's having to move n amount of things up. The linked list, if we wanted to do the same thing, instead of having our pointer to the start of our list being 214, so we can take a copy of 5, but then we can change the start pointer. Instead of 214, we could change it to 256, and instead of pointing to the 5, we start by pointing to the 4, not having to shift everything else up. So we can do some quite good things with the pointers that make it far more efficient to move data around. For example, if we wanted, I'll do it in a different colour, if we wanted to get rid of -2, if we wanted to take -2 away from our list, so we wanted to take this one away, all we'd have to do is change that pointer to the pointer of -2. So instead of there, it points to the next one, essentially cutting this one out, and maintaining -1 goes to -3 next, without having to shift -3 up, -4 up, -5 up, without having to do anything like that. So we have some very positive things that we can do with our dynamic list as well, more efficiently than we can do with our array. Okay, so let's try and put this into action. Let's have a look at this dynamic stack and queue. Just before that, we're just going to see what a dynamic linked list or just a list in C# looks like and how much memory we can actually get out of it. So just got this going on inside of our queue demonstration program. A list in C#, we can just make a list. We can set it as a particular object, so I'll go for integer at first. So it's going to be a list of integers. My list. And we do something very similar to an array. We have to declare what we're in this case. We're declaring what data type it is, and we're also making a new instance of it. But we're not actually setting a size. You notice when we did it with arrays, we would set a particular size. There's no size going on here, and my list, we've got different commands. We can do add. We can add a number to the list, in this case adding 2 to the list. Now I mentioned before that there's no limit to what we can add to a list. Well, there is, because eventually we will run out of memory, and that's what I want to demonstrate to you here. So we've got a while true loop here. So whilst true, and true is always true, so this is making an infinite loop for me, I'm adding to my list. So this is going to add 2 infinitely. And we're going to see that we can't do that. We will not be able to infinitely add to our list. So we'll run the program. Our list is declared. It compiles. And what I'm hoping is that we should get an error after a few months. Right, so it's running, and we do get an error. We get an out of memory exception. That's telling me that we've run out of memory on this computer. So our list is limited by how much memory we've got on the system. But not just how much memory we've got on the system, also what else is running as well. And if I have a quick look at the count, so we've got this number here. So it got up to having this amount of integers within the list. So let's try and read this number. 286,435,456. So it ended up with that many integers inside the list before it ran out of memory, which is a significant amount. But we'll stop the program. So that was ints. And if we change the data type to being byte, sorry, I'll just show you what an integer is before we move on to that. If you didn't already know, hover over it and you find out that it's a 32-bit number. So an integer is a 32-bit number. So that many lots of 32 bits before we ran out of memory. Byte, hopefully you know that. A byte is a byte, which is 8 bits in length. We should be able to run this program and get a larger amount of list items because we're taking up less memory per list item. So instead of 32 bits, we're taking up 8 bits. And again, run my while loop, my infinite while loop, and it should crash. Yeah, the program's running, and adding to our list, and it does stop. This time when I hover over my list and I find out the count, we've still got the same error, out of memory. Copy this number, take a look at what this number looks like. So this time, as we anticipated, we're going to be able to store a lot more bytes because they take less space up. So integers were 32 bits, these are only 8 bits. So in this case, we've got 1,073,741,824 bytes before my computer ran out of memory. Let's not forget that this is, I'm currently running a few PowerPoints and running a image capture software. So you might get different results from this if you run the same test. A little bit of research I did, I found that by default the maximum size that we can have for a single structure would be 2 gigabytes. So even if you stripped as much as you could down and had as little running in memory and tried to run the same test, you would hit a maximum. You can get round that a little bit with 64-bit. That's on a 32-bit system. On a 64-bit system, you can get round that a little bit, but it does end up being limited to a total of 4 billion elements. But when you're starting to store 4 billion items in a list, you've got to be questioning why. And are you programming something right or not? So yes. One thing I forgot to mention that I wanted to cover in this video, so I forgot to mention this at the beginning, I wanted to cover a little bit of exception handling as well. And exception handling is where we're handling what could go wrong, essentially. We've got some exceptions. In this case, we get an error when, well, we will get an error in a second, when we run out of memory, and you'll notice the word exception. So this exception is thrown, it's called, and it's an out of memory exception. So we've gone beyond what we're able to do with this system, and it's just crashed. We can get exceptions through lots of different things. For example, trying to convert a string to an integer when it's not, you've not given the string in an integer format. You've maybe put letters and numbers, letters in there, or symbols, and it would have an exception as well. But we can use try-catch to get around this. We can use exception handling to prevent that. So that's what we're going to have a little look at. So around my while loop, I'm going to surround it with a try-catch statement. So I'm going to write the word try, open the braces, and after this while loop, because that's the part where it crashes, where it tries to add too much, we're requesting something from the heap, we're requesting some memory from the heap, and the heap's going, no, got none available, so it's not able to do that command, and it's crashing. So surrounding it with the braces, and it pops in nicely in Visual Studio to show you that it's within there. And you need a catch statement, and generally you'll see something that just says exception. You can catch a particular exception, and what's going to happen is it will try and do the code in here, but if it's unable to, and if an exception is thrown, it will jump and catch the error. So error, I'm going to write error in there. So what's going to happen, it will continue to add to the list, add to the list, add to the list. When it gets to this error this time, instead of crashing and stopping the program, it's going to catch the error, output this to the console, and then carry on. The program will carry on, and I'll get it to show how many items it's added to the list. So my list dot count. So we declare the list, the storing bytes. We try and have this infinite while loop adding to the list. It will get to the point where we run out of memory, so it'll, instead of crashing this time, it will catch the error, catch the exception, and output whatever we write in here, and then just carry on with the program as normal, as if there was never an error. And it will output to us how long my list has become. So we'll run it. So this is called exception handling, and we use a try catch to help us do it. So the program's running. This time it won't crash. Instead, we just get error being output because that's what we said we wanted to catch. And it outputs, after that, it just carries on with the program. And in this case, outputting the count of items, which ends up being the same count as we had before. It would not be able to add that extra one because we're out of memory. We've got this general exception here, but we could be more specific. Perhaps we could be trying to catch multiple types of error message. So we could have multiple catches here. So we could look to catch out of memory exception. Out of memory. So in this case, what it should do, it should jump to this catch as opposed to this one. We could continue to do this. We could continue to have catches for various different types of error. When we start typing exception, you see the amount of different errors we can have there. Divide by 0 is a good one. Index out of range exception, so when you're trying to access an array position that doesn't exist, whether it's too high for the array or it's a negative number. Insufficient memory exception. There's loads of different exceptions. Overflow exception, stack overflow exception, and you can tailor it. So you can tailor your responses. In this case, we'll just, for this example, we'll just put a divide by 0 one in there. Div. Oh no, I'll just put div 0. So if I run this now, again it should try and do this while loop. When it comes out with the error, because it's an out of memory exception, it should output out of memory. We shouldn't see divide by 0 or error. And it's just showing you there that we could catch multiple different types of error and do different things with them in our exception handling. Run the program again. Program runs, constantly requesting from the heap, trying to get more memory, more and more memory. And we see that it goes to the catch that is out of memory exception, as opposed to divide by 0 exception or just a general exception. It just represents errors. We can be more specific as to what exception we're looking for. And that's exception handling for us. So we are moving on to making our dynamic stack and our dynamic queue. So we'll start with the stack. Did I have it loaded up? I think I got rid of it. So we'll start with our stack and show you how we could change it from being what we had before, where it was a static array, static structure as an array, and we could implement it as a dynamic data structure. So yeah, previously my stack was an array. So once we declared what size it was, once we declared an instance of my stack and sent in a size, it was that size and that size total. We couldn't increase it, we couldn't decrease it. So we're going to add a new class, new item, new class. I'm going to call it my dynamic stack. My dynamic stack. And I'm going to be a bit lazy. I'm just going to copy everything that's inside of my stack into my dynamic stack. We're going to have to change things because the arrays don't work the same as dynamic structures, as dynamic data structures, as lists. But we can essentially have the same things. We're going to have some properties. Or are we? I'm going to comment them out now and think about whether we're going to have some properties in a second. Of course, we're going to have one property at least. We're going to have the actual list itself. And we're going to stay in the same format. We're going to have characters. So a list of chars, stack content. I like the name of it, so we'll carry on with that. And we don't require a size. Also, our constructor has to be the same name as the class. We've changed what class this is in. So my dynamic stack is the name of the class, and it needs to be a public access modifier. Now I'm going to have two different constructors in this case, just to show off the fact that we can have multiple constructors. We can overload the constructors. I'm going to have one where we don't put in a size and one where we do. So I did mention before that we could, if we wanted to, limit the size of an array, of a list. I'm going to show that now. So we make a new instance of the list, and you see we can have capacity. We can set a capacity, so we can do that there. So we can set a capacity to it. However, if we don't send in any parameters, we're going to have it just make a stack that is, a list, that is of whatever size we want. So by default, it's going to make us a list of the default initial capacity, as it says. Default initial capacity. Can we find out what the initial capacity is? Oh, we can find out the total number it can hold. Okay. Interesting. If we go back to our program quickly. These are the kind of experiments that you should do before recording a video. But so we've got a list of characters called A, new list, make it default, and then let's just get it to output the capacity for us, so we can see what we should be expecting. Run that program. What is the capacity? Okay, capacity is 0. So imagine if we add something, add a character A, that will have the capacity 1 then. So our default capacity seems to be some, like, whatever the size of it is. Oh no, it's 4 now, okay. Odd. It so sets the total number of elements. So if I add 4 things, what happens to it then? 1, 2, 3, 4. Sorry for doing this experiment live, but you can play along. Still 4. What if I put a 5th item in there? Does it take chunks of 4 out at a time? So is the capacity going to be 8 this time? It is. So it seems to take chunks of 4. It could be to do with the size of the data type. Let's try and see if byte's any different, and then we'll continue with the video and get it finished. Putting a number in. So is it still 8? It is. So that's something interesting to possibly look up. Why does it keep changing capacity? But if we do set a default one, if we do set a maximum one, let's see what it says as the capacity. We set it as 100. Yeah, so when you do actually set the capacity to be a particular number, set the maximum size of it to be a number, the capacity is then 100. When you don't, by default, it just goes and grabs it as it needs it, and it seems to grab it in chunks of 4, which is very interesting. Okay, so back to the stack. So we've got our list. We can set a particular size to that list, or we can just leave it as default. So that's our constructor. Got our list there and our constructor. We no longer need kind of a top of stack pointer, because in this case, in the list, it's going to be the last thing that was added to the list. So it's whatever the list is size is, -1 would be the index of the last data item. So we can get away with actually only having this as our property, because we can infer what the pointer would be pointing at. It would be pointing to the last item in the list every time. So pushing. Pushing is going to involve adding to our stack contents, and we're going to be adding letter. And just to make sure that we don't crash, we're going to have a try catch. So we're going to try and add to the stack, and we're going to have an exception that gets thrown, out of memory exception. And what I didn't mention before is you could also put a variable or identifier here, and you can get more information about that exception and do more things with it should you require it. So I'm going to do a write line and e.message. So it's going to output what the exception is, what the exception message is. So the push, it'll try and push it, it'll try and add to the stack, and if it's out of memory, it will give us an error message. Fairly easy, no pointers involved now, because the pointer is just going to be the last data item, which we can find using the stack contents length. Popping, how's popping going to be different? Well, we need to make sure that we've actually got something in our list, so we should first go and check is empty. Our list is called the stack contents.count. If the count is equal to 0, it's empty. Get rid of the full, because we don't quite know what the full length is going to be. Okay, so is empty is the count of things in our list 0. Stack underflow if it is. Anything else? Well, we want to take a copy of the last item in this list, and that's going to be the length of this list, and the the count of items -1, because our lists, just like our arrays, the indexes start at 0. So if we had 10 items in our list, the highest item would be index 9. So that's where we got the subtraction there. So we take a temporary copy of that. We don't need to do anything with a pointer. However, we do want to do something else with the list. We want to remove that one. Stack contents dot remove. We can remove at a certain position, and that certain position is going to be the last item. And we can then return our character that we were interested in to pop. Peaking, well, we've already corrected, is empty, so we make sure that we don't peak there, and the peaking just needs to return what we returned when we were popping, but it doesn't need to do any sort of removing. And then that is our stack with our dynamic data structure. Although we're not storing a top of stack pointer, we are calculating what it would be and still using it. And we should test this out. We should be able to do the same tests as we had for my stack. I'm just going to take a copy of these, just like we did for the queues. Static void my stack test. In case we ever want to come back to it. We'll have those, and we can make our another one, static void my dynamic stack test. And again, I'm going to take all of this, do the exact same test. I'll leave the read line there. Take all of this, because that helps us to test whether our normal stack works. So it should be able to help us test whether our dynamic stack works. And just change the object type, the data type, to my dynamic class, my dynamic stack. I'll use the constructor. If you notice, we get to see that we've got two overloads. We've got one where we don't have a size and one where we do have a size. So we'll try the one with no size at first. So it should go on for as long as we want. We won't expect an error anymore, because we can grow beyond what the minimum will be. We'd expect when we peak to get an N. We'd expect when we pop to get an N. The second pop we'd also get an N, because we've pushed all of these on now. The next peak we'd expect an N again. So we've just taken 2 off, and we've still got the third one. Another pop we'd expect N. Another pop we'd expect A. Another pop another peak we'd expect D. We're going to have to add a few more tests. Another pop and another peak. Pop 5 should pop the D. And then we should be peaking at nothing. We should be peaking at an empty stack at that point. So we should get an error. With that as well, going a bit beyond that, we could do the other test that we did before. While trying to think what we can do. Just make a character here, character called TST, test character, and put a T in it for now. Whilst TST is not equal to a blank space, because we were returning blank spaces when we had errors. I want to what do I want to do? No, I'm trying a different test here. I wanted to test whether we could still run out of memory or not, and with that we need to do lots of different pushes. Whilst true, my stack.push. So we're going to break this up. So the first lot of tests should be quite normal, as we expect. Very similar to what we did with the test before. And then this one's testing for us going for an out of memory exception. We're trying to push too many things on. Because we test for trying to take too many things off down here with our peaking at an empty list, and we could try a pop of an empty list as well, so we expect an error there as well. So let's run this and see if it does as we expect it to do. So the program compiles, that's a good start, and the program doesn't do anything because I've not called it again. Always remember to call your subroutines. No reference here. The main was just going to have a console read line. So my dynamic stack test. Calling that subroutine, it'll come down here and do this. Run the program. Do we get as what you expected? So we were expecting n to be output. Yeah, n, 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 n. Yes. Pop 4. We're expecting a. Yes. Then d. Then d. Underflow. Underflow. So yeah, 2 errors. And then if I press enter, this is us trying to push on as many items as we can. And then we should get a load of errors coming through as it tries to go through this infinitely. There we go. Exception type. Notice it didn't crash because we've got the exception handling, but because of my my infinite loop here, out of memory exception. Not crashing though, just outputting that message that we told it to do. So it was outputting E's message, the out of memory exception. Okay, we should do just one more test, and that's testing the other constructor where we set a maximum size. So if we set a maximum size of 2, 3, 4, let's set a maximum size of 4. And let's see how it changes what we expect for the outputs. So we should peak and get n, so this one shouldn't be added. So peak on that end, pop that end. So we'll be looking at that one next. It would pop that one. So we'll be looking at A next. So I'm trying to remember where I'm up to. So peak n, pop n. Pop n, peak, and it's an n, and it should pop n. Sorry, try again. Push peak n, pop n. So we're up to the second of our ends. We pop that one as well. And when we're peaking here, we should be able to see the A, and then we should be able to pop the A. Next one we should pop is D. and then these all should be errors because we don't have that many things. Let's run that and test and see if that does in fact work. Okay, so we do get the information. So N, P2, another N. I just got this wrong myself. So peak in the first one, popping it. It doesn't seem to have worked, not as I intended it to. Let's just have a look why. So I put a breakpoint in here. Let's see what's happened. So my stack has got a count of 4 things, and then on this line we're going to try and push an extra thing in there. So go into here. Stack contents become 5. Okay. I thought we'd set the maximum size. So my idea of setting the size is not what I thought it was. It's not what I told you it was. And when you actually read what it says and not just guess at what it's doing, when it's doing capacity, it specifies the initial capacity. So like an array where we've got, so say if we did 100 with an array, it would make a array size of 100 in memory. The list can also be set up to do that. So initially it would go and get 100 memory locations from the heap, as opposed to what I thought it did, instead of actually reading and paying attention. It didn't do as I thought and set a maximum, and it looks as though we're not able to do that without making an extra data type here, like max list or something. Max list size. And then setting it equal to size here. And then down here on the push, also checking that we've not got a count that's greater than max size list. By default will be 0. We'll just make sure of that. So max size list is not equal to 0, because if it's down as 0, I'm going to have that be our any size list. So it's not equal to 0, and max size list is equal to the count of our stack that's when we can output an error of reached maximum size, which maximum size specified. and then we can put everything else in the else. So the whole try catch error message there, making sure it doesn't go out of memory. So we've bodged it there by using our own data type and making sure that it doesn't go, or it isn't equal to the count already there. So hopefully those changes should have corrected it, and we should be able to have we should be able to get what we're anticipating now. So we shouldn't get this n being added. So yeah, we're getting the output that we just made, maximum size specified, so that's that n not being added. We then get n, 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 a, d, and then the rest are errors. Excellent. And that's where we'll leave the video. So we've added our dynamic data structure to our stack, and we can see how that data structure can grow and shrink, whereas the arrays are a fixed size. And we've seen the advantages and disadvantages of both.